evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IAC. It's my pleasure to introduce today's speaker, Professor Angur Mani. He'll be speaking on distributed online stochastic optimization with myopic agents. Professor Angur Mani is a visiting scholar at the University of Illinois Urbana-Champaign, an affiliated faculty in the Industrial and Systems Engineering Department at the University of Minnesota, Twin Cities, and the founder of Social Ripple Solutions. His research takes an interdisciplinary approach towards efficient design of infrastructure networks and collective decision making with application in sustainable production and consumption, rooted in social and economic sciences, operations research, and computer science. Over to you, Professor.
Thank you very much. Okay, so there is a single agent that has a set of available actions, D, and whenever it takes an action, it gets a reward that has an unknown distribution. The agent doesn't know, right? So the agent has to keep taking the actions again and again and keep accumulating the reward, right? So this is the stationary problem here. The decisions, so the reward distributions do not change over time. Okay. Now, the order of the events will be that agent takes an action based upon its history, and it can decide which action to take, and then it observes the reward and updates the history. Okay. Now, what is the objective of the agent is to maximize the expected cumulative reward until the end of time. Okay. So we are assuming there is some finite time horizon over which the agent has to optimize its aggregate reward. Okay. Now, traditionally, what would an agent do? It would learn the reward distribution early enough by experimenting. Okay, they can try different actions, see what is the reward distribution estimates, and then based upon those estimates of the reward distribution, it can actually optimize the rest of the time. Right? That would be a good strategy for the agent. We're going to put a twist in it. Instead of single agent, I will have many agents, right? And what I'm going to do is that I'm also going to make agents myopic. So from the perspective of the agent, it is not going to optimize over the whole time horizon. It's trying to optimize the instantaneous reward the next time step. Okay? There are two formulations that I'm going to consider. I'll spend almost all the time in the first one. It is slightly simpler, and the second one I'll give insights into what's going to happen in this case. So the first formulation is the multi-armed bandits formulation, where the set of actions is discrete and finite. Okay? So the D is finite, and the rewards are also independent across different arms, different actions. Right? So this is the first paper that's coming out in OR and appeared in EC last year. And the second one, it's a much newer manuscript we have, in which I'm going to consider infinite decision space. So decision space here is, in this case, is really a polytope. Okay, and the rewards again naturally are going to be correlated. Right? So this will be a slightly complex setting, but I'll give you the insights from this paper, and I will hint about how it actually extends to more complex spaces, decision spaces. Yes. So think of a polytope, right? And think of an LP problem where decision space is polytope and your reward is the dot product of your decision with a vector that is unknown. Right? So the rewards across different vectors will be correlated in this case. Right? Okay. Now, though in that case, the vector, the coefficient vector with which you are taking the dot product is unknown. That is something that you have to recover. Okay. Any more questions? Okay. So let's jump in. Now, this problem of going from a single agent to multiple agent has received a lot of attention over the last decade. And this is because in many situations, central planners do rely on experimentation by independent agents. Right, let me give you a few examples. The online platforms like Amazon, for example, discovers the quality of the products, the merchants, by users rating them. The users have to experiment with different products, different merchants, and they can rate them. Right? And that has been driving, this kind of problem has been driving the attention to this problem for quite some time. Right? And this has become more relevant with the arrival of agentic AI because these agents are representing individual people and they have fiduciary obligations, may have fiduciary obligations, for example, in financial systems and so on. Okay. Now, what I'm going to be more interested in is something of much higher societal value, right? And this is the more recent work that I'm working with my colleague Torge Iyer at Georgia Tech. And the problem is as such. In 2018, the US House of Congress, US Congress passed the Right to Try Act. What it does is that allows patients, often terminally ill patients, to try treatments and drugs that are not approved by the FDA. So they have gone through phase 1 trials, so they are safe, but they have not gone through phase 1 trials, phase 2 trials, so we don't know the efficacy of these drugs. Right? So that is the scenario. So now what actually happens is that these patients, often terminally ill, are going to contact their physicians, and physicians are going to prescribe drugs to these patients. Now, this is a very interesting case because the physicians are not experimenting with these patients. They cannot experiment with these patients. These patients are not participating in a trial. Right? So these are regular patients. Physicians have to do the best for the patient in front of them, given the information the physician has. Okay? So in this case, think of these patients. You have a sequence of sequence of patients coming in. Physician takes and gives a drug to the patient, sees how the drug performs. If it performs well, continues to the next patient. Doesn't perform well, tries the next drug, and so on. Right? Yes. Yeah. No. Let me finish this. I'll tell you why. Okay. So this is what the physician is going to be myopic, right? Is going to do the best for the patient in front of it, given all the information it has. It is not going to experiment with the patient so that it can do better for the next patient, right? So this is what the physician's dynamics is going to be. Now there will be multiple physicians, right? They all will be doing something like this. Now under the bill, all the physicians have to do report to the pharmaceutical companies who actually give these trial experimental drugs to the physicians, and pharmaceutical companies are required to report it to FDA. Right? So FDA is kind of central planner, is observing everything. Right? Okay. So FDA is relying on these physicians to learn about the efficacy of the drugs. Okay? Where what makes problem complicated is the physicians are not experimenting. Right? The decision is not motivated by learning. The decision is motivated by outcomes, immediate outcomes. Okay? Now, there are other scenarios where these things are also relevant, which is like selling through independent agents, right? So in India, for example, there are secondary sellers from Amazon. So they are these agents who actually get products from Amazon and then they sell them in villages. Right? So these are small businessmen. They don't want to experiment. They want to rather rely on high quality evidence and take good actions. Right? Yes. Yes. Yeah, so central planner wants to do the best for all the patients that will be coming in the future. So I haven't formulated it yet. Let me do that. I'm just giving a little bit high level overview. Okay, let me answer your question that why the myopic policy is not optimal, right? For a single agent, right? Okay, so suppose I have two actions, right? So one, the expected reward from one action is 1, the other one is 2, right? Now the myopic agent comes, it pulls arm 1, reward is 1, right? And so initially the beliefs of both the arms is 0, right? Let's start with 0, right? It takes action 1, reward is 1, it keeps taking action 1, and suppose the sample path, which is like will be around 1, and say variances are very small, for example. So it will very likely, with very high probability, it will never pull arm 2. They will never know that arm 2 was better, right? So the myopic agent will not do. So a forward-looking agent will also try arm 2, right? Even if it sees arm 1 is giving more than 0, right? Yeah. Okay. Okay. Good. So this is the framework we are going to look at. Okay. Okay. Now let me give you an example, a motivating example, which is of very high value, which kind of motivated me to look at this problem, right? So if you look at, if you do a Google search, and AI gives you a good overview. So how long did Moderna take to create the vaccine after the gene sequence was released by China, right? And turns out that gene sequence was available on January 11. On January 13, Moderna had the sequence for the vaccine. They designed the vaccine. So it says 2 days. It actually took like 9 hours for Moderna to actually create the vaccine, design the vaccine. Now there is a long wait for production and first dose administered for phase 1 trial for safety and so on, right? And it took a long time because it has to go through RCT to get EUA approval. And after testing 30,000 volunteers, on December 18, 2020, emergency use authorization was provided. Between this time, the number of lives lost just in the United States was about 500,000 people, right? So the value of like studying this problem is immense. The societal value is actually immense. Okay, so let me just show you what actually normally is done in centralized experimentation, and why those techniques are tricky and often not good. Or I'll say not good. Well, at least in certain scenarios, what we are considering over here. Okay, so let's see what the central planner can try to do. Okay, so there are two approaches often taken, and this list is very small. There is a long line of work that has gone. I'm just pointing a couple of them over here. So two approaches taken. One is incentivizing exploration, right? And often in the context of marketing and sales, you can actually incentivize the sales agents to explore, right? And there's a lot of work that has been done. The other line of work is information design, which is mostly Bayesian persuasion in this context, where you kind of lie, you actually manipulate, right, by giving wrong information. Often, sometimes you can actually give the wrong information. Most times you can give the good information. And the motivation for this problem early was the Google Maps and Waze platform. Now, recently there is a departure from that in information design that happened done by Mollica et al., where they actually did something different. They actually created groups of agents who can observe each other, right? And as time goes on, those groups were restructured and so on. But it became very complicated, right? And turns out the number of agents they needed to for this to work was in the order of quadrillions. So I'm not sure how many quadrillions are there on this planet. So it is problematic, right? So our work can be seen as an information design, but in a much simpler information design situation. I will show you why and how it will work. incentivizing exploration is completely out of the question, especially when you're talking about giving doctors incentives to prescribe drugs, although it is a common practice in places where Parimal and I come from, but and maybe other places too. But it is not feasible. Okay. Now the question I ask is, can a much simpler control work? Right? And the control I'm saying is that if a central planner has this blunt control of, say, discarding arms irrevocably once it considers that arm to be suboptimal with enough confidence. Okay? And this is the control I'm going to work with, and see if it is good. Okay? Now you can also think of it as a simple information design where there's a broadcast signal being provided to everyone saying that this arm is not good. Right? Okay? Now there is no manipulation, it's the honest information being provided over here. Okay? That when I have enough confidence that this arm is suboptimal, that's what I'm telling everyone. Okay? Okay, so let's look at the model. Now let's coming to the model. Let's give an overview first. So consider the firm that has an assortment of products, or there's a pharmaceutical company. There's a list of drugs that it has. Okay? There are agents that make selling decisions, or physicians that make prescription decisions. Right? So each agent will have the same set of arms here. Now I'm going to change terminology here, getting into the bandit framework. So these are the arms. The firms make the arms available. Each agent has the same arm, same set of arms. Okay? Once the agent discontinues the product, all the agents discontinue. They cannot use that anymore. Okay? So this will be the model. Okay, so now let's get more formal. So I have a central planner that has set J of arms, right? And makes a subset JT at time t to I agents. Right? So JT is a subset of J, right? That is available to agents. Each agent makes its own effort allocation. Now the cumulative effort spent by agent I until time t will be given as this vector, where this vector consists of the effort allocations on all the arms by agent I. Now, what I'm doing here is that I'm modeling this in continuous time, right? Which is not traditionally done in the bandits literature. But if you dig further back, there was earlier work in this, right? So Avi Mandelbaum did this in the 80s. And it's funny because when I was doing this, Abi was visiting, and I had some identities to study this continuous time bandit framework, and I was very excited. I was saying, Abi, I have something really cool here. I think, what do you think about it? And then he pointed me to this paper and said, look, kid, I did this 40 years ago. Yeah, so I haven't told you what class of controls will we use. But right now, just say JT is just some arbitrary set, right? Yeah. So now the agents spend this effort, right? Which is dependent upon this is the measure of time they have spent, a measure of effort they have spent across this whole time. Okay. Now I have this condition that the set of the sum of the efforts across all the arms is equal to the total time that has passed. So the rate of effort is actually 1 across all the arms. Okay? Okay. Now, once an agent puts an effort on the arm, for a cumulative effort S, the reward that accumulates from arm J is Rij of S. Okay? Now let's see how Rij functions. So the rewards of the same arm from different agents are correlated, but in a particular way. So in a particularly, we call say mu j is the drift of arm j, right? And the reward has this form, where so the reward from arm j to agent I, having spent effort S, is mu j times S plus some Brownian noise. Okay? Then so all this only grows if S grows, right? If the effort grows. If the arm is not being put any effort, the reward accumulation does not happen, right? So there are two concepts of time here, right? There's the effort and there's actual clock time. Okay. Okay. So if you have worked on stochastic processes, you will have seen the subordinate processes, and so that's what actually is going on over here. Yeah, because you're going to get reward only if you are putting effort in an arm. Right. Yeah. So this is the reward only from arm J, right? You will have accumulated reward from other arm. So aggregate your noise is being accumulated at the rate of. They're all, yeah. That's correct. Yeah. Yes.
Seems like rested case where once you don't put effort in that sort of state, it's not moved.
That's correct.
Some circumstances actually be the case that when you don't put effort in it, it still continues to go on. In discrete time, we call it the restless.
That's correct. Yes, you can do that. So so I have not done in the distributed setting, but in a single agent setting, there is another paper that I've worked with Lavanya Marla at UUC and a student Zitao, where we actually studied sampling airspace, where the so the flights are going, the airplanes are going through airspace. We're trying to look at the headwind. So headwind, even if we are not sampling, it's changing. So that's a restless situation. But there's a lot more structure there, because yeah. Yeah. Yes, yes, the state is changing. So I haven't talked about the state yet, right? Because the state, so I have to define the estimates, and that forms the state over here, right? Yes, so the states do not change, and the underlying reason is that we're trying to look at the efficacy of the drugs, right? So we're looking at for a population on average how the drugs will perform, right? So they're yeah, but there are other scenarios where it can actually happen, yes. Yeah. Okay, so now the Brownian motion is independent for each arm agent pair, right? So you're not learning anything about other arms if you are only pulling one arm. Okay. Okay. So now let's look at how the agents process information. So agent maintains an estimate of the drift of arm J. Right? Now the estimate of the drift is just that cumulative reward accumulated from that arm divided by 1 plus the effort put on that arm. Right? You can think of it as the Bayesian estimate, assuming a prior of mean 0 and variance 1, or Tikhonov regularized estimate. So. And then, so this is what the agents do. They only observe their own information, right? And they make these estimates. So the central planner, on the other hand, observes everything, all the rewards and all the efforts of all the agents. Okay. Now there is a misalignment between the planner and the agents. Center planner is forward-looking, and it wants to optimize over the all set of agents, but the agents are myopic. They're not just like individual, they want to optimize for themselves, but they also want to optimize for themselves in the moment. Right? So it's as bad as it can be. So in this case, what do the agents do? They will put all effort on the arm with the highest drift estimate almost everywhere. That's what the agents will do. Now central planner, on the other hand, wants to optimize this. Cumulative reward over the whole time period or time horizon across all the agents. Right? So the two extremes here. Now, in this case, we are going to talk about what are the main questions and what we want to achieve. Right? So suppose we want to, so let me first define the metric. So we are interested in expected regret. Right? What is the expected regret here? So here the expected regret, so assume B1 is the arm with the highest drift. If everyone knew what the arm's drifts were, then they will pull arm 1, the arms with the highest drift. This would have been their reward. I, which is the number of agents, time mu times t in expectation. Okay? Now, given they don't know and they use whatever thing they do, the total aggregate reward they obtain is this. Right? Total aggregate reward they obtain is this. So the difference between this is the loss due to the lack of information that they have, and that is the regret here. Okay? Now, let's see, put a benchmark. If the central planner can control the decision of all the agents, right? So one policy would be is that at each time central planner puts only one arm, right? And then everyone has to do that, right? Then this is like a centralized single agent problem, right? So in this case, the regret, the worst case regret over all possible realizations of the drift vector mu, right, is going to be at least j, which is the number of arms, times log times it here being the effective horizon. Right? You cannot do better than that. That has been established as early as in 80s, Lyon Robbins. And the idea is very simple. If you sample each arm log it times, right, the confidence intervals of those arms will be very small, and then after that you can just keep the arm at the highest expected estimate. Right? And in this case, the error that you will make will be very small, and multiplied by the time remaining you have, you are still controlling the error. So you are balancing the error with the amount of experimentation you actually do. Right? And they will be the same rate. That's why you actually get this regret. Okay. So now question is, can a central planner's strategy of dropping arms achieve this regret bound? So now this is the policies we are looking at. So it's a shrinking set. So JT is a shrinking set. As time grows on, we cannot add more arms. So arm once removed can never be put back. Right? And then the important question that comes is that how many agents are needed to achieve this regret bound that you want to achieve? Can we achieve this regret bound? And when can we achieve this regret bound? How many agents are needed to do that? Yes. Yes. Yeah. Yeah.
So here the control, there is still some sort of centralized control. Centralized control is terms of you can choose what you source. But one could go back and think about also because people are involved. Central planner has a lot of information, and ethics would say that to share the information. Central planner is doing it in terms of this control, but maybe are there other schemes or what we call questioning beyond the
Yeah.
specific formulation, which I think is interesting.
Yeah.
But given the drug's perspective, should one think of the best possible signal that will go reach myopically?
Yeah. Yeah, so you can give differentiated signals. So the problem is not, definitely there are much better things you can do. And in fact, talking to the pharmaceutical companies, there is a whole can of worms that opens up when we do that. The problem is what is actually legally allowed. It's hard. It's actually, so the thing is that we are not operating in the experimentation regime here. We are not entering the RCTs. So RCTs also, the RCTs actually are very inefficient, right? From the perspective of the patients, right? So they can be given placebos, for example. Then on the other hand, all the information is kept hidden. There's no analysis or no statistics being done on the information until all the trial is completed. right? There is more recent push towards online decision making in RCTs, but with a strong pushback too, right? So there's a huge huge inefficiency there. Yeah, yeah.
Is that even in an RCT, one could say that the central planner is bound to share the partial results, but still they don't do it.
So no, they're not bound to do that. In fact, they cannot share the partial results. Yeah. So here, what I'm saying is that I'm sharing slightly more information. That actually, because I have that ability to do that because of the RTT. So it's not operating an RCT, it's an RTT now. So I have something that I can do. Yeah, okay. Okay, so right, so these are the two main questions I'm going to answer here. Okay. So first let me tell you a little bit on why we choose a continuous time framework. This is not traditional. By the way, it is not traditional because most of the progress that has happened in bandits actually came from computer science. Right? It's not because it's not more powerful to do it in continuous time. It's actually way more powerful to do in continuous time. I will show you that we can actually get results, lots of closed form results that we can actually get that we cannot do in discrete time. And we can avoid all those boundary conditions of jumping from one arm to another, right? So all those things, dynamics are well handled in continuous time because the switching that happens, it happens in local time, right? Okay, what happened here? Oh, I'm sorry. Which one? Oh. Okay, sorry. Okay, thank you. Okay, so let's look on continuous time model. So one thing that actually comes really handy, and I will encourage you to look in the paper, is that there's some nice equivalences that we have established between effort allocations, allocated effort, and the escape time of the drift estimate process, right? For special nonlinear boundaries that actually get, right? Now, because of which we can actually write the Fokker-Planck equations and solve for the distributions of efforts, right? And thus provide very fine results. Let me show what kind of results we can provide, right? So let's talk about regret under different settings, right? So let's consider a single agent without a planner, single myopic agent without a planner, right? Now, the regret of the single myopic agent is going to be linear in time, and it depends upon the probability of not settling on the best arm, right? Right. Okay, it turns out that this probability of not settling on the best arm, I can actually get closed form expression for that, right? For a single agent. Okay, you cannot do this in discrete time. It becomes very complicated. You can probably get a series, and it may be hard to get what the series actually converges to. Now, single agent with planner, right? Let's consider single agent with planner. Now, this is a very interesting thing, because if you have only one agent, turns out that if the central planner does anything, which is removing arms, it is going to make things worse. And this is the reason why. Suppose the single agent is pulling arm 1, right? Then that arm is more likely to be the best arm than any other arm at the moment, given the information you have, right? There's no point removing that arm. And if central planner is going to remove another arm which is not being pulled at the moment, you can always wait until the agent starts pulling that arm, right? So there is no benefit of removing that arm at the moment, right? So because of which, the best action for the central planner with one agent is to do nothing, right? And then in that case, you have the same regret, right? Now let's consider multiple agents, right? Now the things become more complicated here, right? So let's find out what actually happens with multiple agents. Okay, let me first introduce some definitions, and then we'll see how introduce a policy and then see what will happen in that case. What kind of policy central planner can actually choose. Right? So first, I'm going to introduce a confidence interval, confidence bounds. So for each arm, I will have an upper confidence bound and a lower confidence bound. So this is the standard empirical estimate here, and then I have the buffer. So one thing that I'll see is different than what you have seen in say UCBs is actually this factor, right? The second term over here, right? Second term over here. The reason I have this second term is that unlike UCB, where I have fixed times where I can actually make decisions, right? I'm going to need adaptive decisions, where the time of decision making is not pre-decided, right? So I have to choose confidence bounds which is slightly more conservative, right? And it is going to be valid all the time. Okay. Now I am not choosing the confidence levels over here, right? Confidence levels are going to be chosen based upon the horizon that I have. Longer the horizon, the more confidence levels I need. Okay. Okay. So now let's say the behavior of these two things. So what I want is that as the effort grows, I don't want this large of a buffer. This should not be very large, which is okay, right? Because this first term will dominate as effort grows. I want to be conservative near very small amount of effort. That's why I need this term over here, because near 0 it explodes much faster than 1 by square root t. Okay, and turns out this gives me sufficient buffer to work with and without compromising the regret that I need. Okay. Okay, so given these confidence bounds, so if I look at the supremum and infimum of the confidence bounds, they will look something like this. As the effort increases, it starts converging near the true drift. Okay, so now given this confidence bound, I'm going to define something called an anchor rate, which is the highest lower confidence bound over all the arms for the central plan. Now this is all from the perspective of the central planner, right? The confidence bounds are provided for the central planner, which is observing all the rewards and all the actions of all the agents. Excuse me. Okay. So now this is my anchor rate. The interpretation of the anchor rate is that going from now until the end of time, the central planner expects to have the reward rate no less than this anchor rate. Right? No less than this anchor rate. Now, given this, central planner's policy will be something like this. So it will have this anchor rate process. Any arm whose upper confidence bound falls below the anchor rate is going to discard that arm. Okay, because the central planner knows that this arm will not give me the reward rate, which is the anchor rate, at least as much as the anchor rate in the future. We can discard that. Okay, so that in the example here, so consider this solid arm and the dotted arm, right? This is the upper confidence bound. This is the lower confidence bound. So if this is what is going on at this point, the arm. The dotted arm will be discarded, right? So this is how the policy will work. Is it clear? Okay. Okay. Now, with this policy, there are two sources of error that I have to control. Right? The first source of error is that the arm with the highest expected drift is discarded, right? Which is bad. The second source of error is that the anchor rate stays low for a long time, which could be the case if good arms are not tried, right? If only all the effort goes in the bad arms. Okay, so let's try to control these two errors. Right? So first error is slightly easier to control if I have my confidence bounds very well behaved. Right? So it turns out that if I have my confidence, with very high probability, my confidence bounds are very well behaved. Right? So with at least this much probability, the true drift of the arms lies between the upper and lower confidence bounds at all times. At all times is the critical phrase here. Okay, so now, that's good. So if that is the case, then as a corollary, the probability that the arm with the highest drift is discarded is at most this much. So log IT by IT. And that is the maximum probability that the arm with the highest drift is discarded. So that error, the amount of regret that error can actually introduce is at most log of IT. Right? You can multiply times IT, that's the maximum error. So with that error is controlled. Okay? Let's try to control the other error, which is the nasty error to control. Okay? So now, the main result actually says that if I have at least 12 log T agents, and this is actually a critical number here, if I have at least 12 log T agents, then by this time, here alpha square only grows log of IT, right? So by this time, and where delta is also the minimum difference between the drift of any two arms, right? The arms have to be well separated. So we have sufficient number of agents, and the arms should be have some separation. Okay, so if this is the case, right, then by this time the anchor rate is actually very close to the top arm. Right? Now, what actually would happen if the anchor rate is close to the top arm at this time? Any future time, no other arm can get enough effort, because if they get enough effort, their upper confidence bound will fall below the anchor rate, right? So they cannot get enough effort, and if they fall below the anchor rate, they will be discarded. Yes.
So you're in working continuous time.
Yes.
So in the basic time, there is a notion of pulling arm and sequence. Here, what is that? Because you're gonna pull an arm for a certain amount of time. At the end of it, you're gonna update your confidences. I don't understand.
Also, the whole process of the confidence bounds are also the process, the continuous time process.
Every time you're doing it.
At all instants, yes, yeah. So what I'm saying is, if the anchor rate has come up to here by this time, then the amount of effort it will spend on all the other arms in future cannot be more than logarithmically in IT. Right? Now let me show you what actually happens. Something like this happens, and this kind of gives you the overview of how the proof will work. So if I have I agents, then by this time, right, there will be at least one arm in the upper half. If I order the arms according to their drift, right, at least one arm in the upper half of the arms will have enough effort, log IT effort, right? Given that, it means that its lower confidence bound is at least delta, at most delta from its true drift. Right? This implies that no arm below that in the lower half will get enough effort after that. Right? So it means that I can actually, this becomes the first critical point. Right? So if I constrain the amount of effort the lower arms can get, then I can go to the upper 1/4 of the arms. Right? And I can keep doing that. Right? So that by this time, the first arm will have enough effort that the anchor rate will actually be at least, so its lower confidence bound be at most delta away from its true drift. Right? So I have raised the anchor rate high enough by this time. Now, one important thing to note about this thing is that, see, I'm saying I is 12 log T, right? Alpha is also log T, alpha square is also log T, right? So this thing is actually constant in time, doesn't depend upon time anymore. So the learning time is constant, right? So in traditional single agent bandit, learning time grows logarithmically in time, right? But here we have a funny thing, like you're learning in constant time. Right? The reason this happens is that the policy actually distributes experimentation across agents instead of across time. Right? And you are able to do that by giving shocks to the system. Every time agents are starting to settle on an arm, right? Given at least two agents are in two different arms, you can remove an arm, giving shock to the agent that was pulling the bad arm. And that when the agents, that arm is removed, the estimates of all the remaining arms for that agent is the same. And that is the time where experimentation happens. Then that jump starts experimentation, and again you can remove one arm and keep doing that. Right? So because of that, you are able to learn in constant time. And now one other thing I want to say is that because of this I being in the denominator, this constant time keeps on shrinking reciprocally in the number of agents you are adding. Right? So the amount of experimentation stays the same, right? Just that if you keep on adding more agents, you will keep shrinking this time. Right. So now finally we can, using the previous theorem, I can actually constrain put an upper bound on the expected effort on suboptimal arms, right? Which is going to be like this log of IT. Right? Log of IT, and this term is going to be dominated. Right? So we can ignore that. Okay? And because of that, my regret is also going to be same rate. Right? Now here I'm going to put the worst case thing over here, constant over here, but you can actually keep on refining it. In fact, one of the reviewers asked us to say, okay, maybe you can say a little more. So we are doing that. Okay. So so that was the positive part. Let me give the negative result. Right. So turns out this log t is the critical rate at which number of agents should be added as the horizon increases. If you do less than that, you cannot achieve that, right? So if the number of agents it as a function of time, right, is dominated by log t, right, then for each of these mu vectors, now not all equal, the regret will dominate log t. And you can, under any policy, it's not just this policy, under any policy you can show that. Right? Okay, so let me summarize this part, and then let me give you a overview of, unless there are questions, and overview of the LP problem. Is there any questions here? No? Okay, so let me summarize. So there's a continuous time multi-arm bandit framework with numerous myopic agents making independent decisions. The main results are that if the number of agents grows slower than log t, then a sublinear regret cannot be achieved by discarding arms. If the number of agents is at least 12 log t, but you can actually play around with this number, right? You can, but I don't think you can change the order because we have this negative result. Then O log t regret can be achieved. Okay? And learning occurs in continuous time, and learning speed grows linearly in the number of agents. Right? Okay, let me say a little bit about this LP problem. So here the agent chooses actions in a polytope, right? And this is my the SDE for the reward process. The only difference is that here you say mu transpose xt, right? That is your expected reward. You don't know mu, right? You don't know the mu vector that you want to discover. Myopic agent is just going to choose the corner that actually maximizes, bless you, that maximizes this dot product, right? With the expected mu, right? Now this has a very interesting dynamics in itself. Even if the myopic dynamics in this case is quite interesting. I'll encourage you to look at the paper. It has very nice geometrical properties that was not trivial initially, right? Now here the planar's action space we're looking at is when it actually restricts the polytope, right? So in general in LP there are lots of ways the LP optimization we do the polytope restriction, like the cutting plane and all those things we actually keep on changing. This is slightly different over here. Right? And the goal of the online LP is often to reduce the regret and make the regret not depend upon the size of the polytope or the number of coordinates of the polytope. Right? Because the LP can have very large number of coordinates, and that is the problem. You don't want that to happen here, right? Because if you apply the bandit algorithm here, it will not work. It will not work because there is a j, which is number of arms that becomes as a regret constant, right? We don't want that, right? So in online LP, the benchmark is that the regret grows linearly in the dimensionality of the polytope. Right? We want something like that over here. So I'm not going to do that. I just want to show you a picture that will give you the best idea. Right? So what is happening is that the agents are pulling these arms. Agents are picking vectors in the polytope or the corners of the polytope that maximizes their expected utility in the moment. Central planner is observing everything. It is maintaining a confidence ellipsoid of the true mu vector. Right? Now, so this is the confidence ellipsoid for the true mu vector. Right? This is your origin. This is what the central planner is going to do. Right? It is going to project. So if you look at the direction of the center of the or the expectation of the mu vector, right? In the subspace orthogonal to this direction, right? It will project this ellipsoid. Look at the principal components. If the principal components along any direction become small enough, and that small enough is a critical factor that depends upon the length of the time horizon, right? Then what is going to do is going to say that, okay, mu, the component of mu in that direction is going to be very small. Right? So in that case, it is going to project the whole problem in a subspace perpendicular to that direction. Now, why this works is that assuming that the decision was correct, that true mu was actually orthogonal to that direction, then projecting the whole problem in the subspace did not change the problem at all. Right? So now one interesting thing is that this is a floating coordinate system here. Right? Everything is with respect to this direction, right? Which is the current estimate of mu. Right? So this works well because again we can actually show that through this process I can actually eliminate the directions, right? But the directions are not known, unlike the bandits, where the bandits' arms were known. Here the directions are not known, but I'm making sure that the error being introduced is being controlled. Right? And through this we can actually show that regret only grows linearly in the dimensionality of the problem. Now there is a lot of work. I just want to conclude. We are right on time, right? So just there is a lot of some new work that I'm working on with distributed experimentation with information sharing over sparse networks, which is quite interesting. Here I don't have a central planner, but I'm saying that how does the information sharing and the time, in fact, in particular, the time of information sharing can impact the outcomes for the agents. Which could be interesting. I'm happy to talk more about it later. Right? And then several other applications in drug testing, revenue management, distributed sensing, path planning. They all actually have some of these things that we are working on in different settings. Okay, so I will just stop here. I thank you for your attention and take questions. Yes.
Thank you, Professor, for accepting our request and delivering an interesting talk. Are there more questions from the audience?
Yes.
The exact term.
The confidence bounds?
Yeah, I think using the confidence, anchor it, yeah.
Oh, anchor it, okay. Yeah.
So, here, like, why are we using soup rather than the latest lower confidence bound?
Soup is much easier to handle.
Yeah, I get it's monotone, but shouldn't we be using the latest confidence bound?
So,
like just from engineering perspective,
it's much difficult to deal with that process. If I take the upper envelope, so I am drawing the upper envelope over here for the lower confidence bounds, right? Okay. This is much easier to deal with. That process is much easier to deal with.
So is it theoretically or as an engineer?
No, theoretically.
But as an engineer, what would I do?
Oh, so the lower confidence bound can go up and down, right?
That's correct. So I should be using the latest lower confidence bound, right, rather than the soup.
So you can actually show the properties will be similar, right? But it is a much more difficult process to manage.
use like in between values. So then I would have understood.
No, no. But the thing is that if you do that, your results will not change. You will get the same regret, right? But this is a much well-behaved process to handle, right? So like in general in probability and stochastic process, there are like very complicated processes that you can actually deal with, right? But you have to choose, right, what are much easier and tractable to handle, right? Yeah. I think most of the art is in actually choosing that, right? Once you have done that, then you're good, right?
Thanks.
Yeah. Yes.
So when you, yes, exactly the slide. So the 1 by t term here, you mentioned that that's for handling the anytimeness in the decision. The decision, when we are making decision, that time is random. So to handle that,
Yeah.
but the same thing also happens in the usual bandit setup because the number of pulls there are random, right?
Yeah.
So how is this different from? This looks more closer to me to empirical Bernstein type of inequality, maybe for the continuous version where we are trying to handle the variance, small variance or large variance.
Exactly. So at the time when the effort is very close to 0,
Right.
that's time. So the first term will not give me sufficient band, right?
I see. Okay.
So that's why I need that. Yeah, exactly.
Okay.
Yeah.
Okay.
And so I may, if I just go with the first term,
Yeah.
I may end up discarding arms way early,
Okay.
right? So and because I don't know when I'm going to discard the arm. So if in case I discard the arm early, using the first term, that will be disastrous. That's why I need more buffer. And this buffer becomes very small because around after 1, effort of 1, this first term starts dominating. So.
Thanks.
Okay. Thank you very much.